The following content is supported by victoris.org.
Now question 7, we're given a helicopter and a detailed diagram of the helicopter blade. In part A, we're asked to calculate the moment of inertia of the blade about the x-axis. The x-axis is over here, which means that we're interested in finding the rotation about the x-axis. This looks like the classic moment of inertia of a rectangular plate question, but we're asked to obtain it from first principles. So how do we do it? First, let some quantity be the mass per unit area. This can be expressed in terms of the total mass divided by the area, but we'll do this substitution later. By first principles, we know that moment of inertia is integral of r squared dm. dm is a small mass element of the body we're interested in finding the moment of inertia for, and the integral is integrating over the entire volume of the object. Now, whenever we have a dm, we need to find the parameterization of the object that is meaningful to integrate over to do the math. In this case, I choose the parameterization using Euclidean coordinates dx and dy. This means that for the dx integral, which we are integrating from minus r to plus r. For the dy integral, we are integrating from minus c over 2 to plus c over 2. Now, what is r squared? For any small amount of mass over here, r is the distance from that mass to the axis of rotation. In this case, it's just the y coordinate. In this scenario, it is simple, but in more complicated scenarios, where you use polar coordinates, you need to be more careful. Now, doing the integrals will give us the following expression, and substituting the mass per unit area, the expression we just got, would give us the correct moment of inertia about the x-axis. Now, we're asked to determine a similar expression for moment of inertia of about the y-axis, and we just need to repeat the same calculations as follows, which gives us 1 over 6 mr squared. Now, the vertical axis theorem is a theorem for planar objects. If you have a planar object, the moment of inertia about the z-axis is equals to the moment of inertia about the x-axis plus the moment of inertia about the y-axis, which is another perpendicular axis. You can see that x, y, and z form set of orthogonal axes, and that's why it's called the perpendicular axis theorem. The plane must span the xy plane. This allows us to just combine the above two results we have obtained to get the following expression, after factoring out the common factors. Now, part 4 is just a matter of substitution, and part 5 is just following the definitions. Following the definition for angular acceleration, we get this. Following the definition for torque, we get this. Because torque is force times distance, the unit for torque is Newton meters. We're given the following equation for the lift on the blade element, and we're tasked to show that the coefficient of lift is dimensionless. Calculating the units for both sides of the equation, we can show that the unit for the coefficient of lift is dimensionless. A few comments over here. One is note that the unit of d is dimensionless, so the unit of dl is simply the unit of l. D over here just means a small contribution to the total lift, and dl is the thing that we integrate to obtain l. Same applies for dr. The unit of dr is just meters. Now, from the expression they give us, dl, we need to find the total lift generated by the two rotor blades. L is just the sum of any tiny contributions dl. And why do we need to do a sum? Why do we need to do an integral instead of just multiplying it by the length? It's because the lift of each small part of the helicopter rotor blade is dependent on how far it is away from the center axis of rotation. So what that amounts to is just integrating the expression they have given us, and we need to find the correct bounds for integration. In this case, because we're integrating the value dr, we need to basically find the endpoints of the value for r. In this case, one endpoint is over here, which is minus big R. Another endpoint is over here, which is plus big R. So that explains the bounds for the integration. Doing the math, we obtain the following expression for lift. Coning is an effect where the rotor blades of the helicopter tilt upwards from the horizontal. We need to explain why coning occurs. This is the explanation, and it's roughly because when we take a look at the helicopter rotor blade, the rotor head is maintaining the rotor blade connection to the helicopter over here. However, the lift will exert some amount of torque on the rotor blades about the rotor head, and that will mean that the blades will effectively form this cone shape. Now, we're given that the coning angle is 10 degrees, and we need to find the angular velocity of the helicopter blade in order for the helicopter to remain in equilibrium in air. For it to be equilibrium in air, we need the net force to be equal to 0, and the net force consists of the mass of the helicopter as well as the lift. If we take a look at the force body diagram, we can see that each rotor blade is tilted at 10 degrees, hence the lift vector will be also at 10 degrees. This explains the cosine 10 degrees over here. Now, just substituting in the value of L, which we obtained previously over here, we can get omega in terms of everything, and substituting in the values, we get 1100 RPM. Now, part D is a long qualitative question, so you can pause the video and read it yourself, but I'll try to explain it in terms of words. Why is a tail rotor necessary for stable flight? In my own words, it's because if you consider the body as a whole, and imagine we remove the tail rotor, I'm going to show you that without the tail rotor, the helicopter body will actually be spinning according to conservation of angular momentum. So it goes like this. Since the helicopter body must apply a torque on the rotor blades to keep it moving, by Newton's third law, the rotor blades will actually apply a torque in the opposite direction on the helicopter body, and that will cause it to rotate. Another perspective is that if we consider the total angular momentum of both the rotor blades and the helicopter body, we see that because none of the external forces applies a torque on them, the total angular momentum must be zero. Since the rotor blades pick up speed, that means that in order for the total angular momentum of both the helicopter body and the rotor blades to remain zero, the helicopter body must have obtained the same angular momentum in the opposite direction, which means that the helicopter body would be rotating, and that is uncomfortable for the user. Adding this tail rotor in, it will provide a torque necessary to increase the total angular momentum of the entire helicopter, and this torque is effectively transferred over to the rotor blade such that the rotor blades can rotate and the helicopter body can remain unrotated. Now, whether the main rotor blade rotates clockwise or anti-clockwise, we can deduce it from the following information over here. We see that the rotation of the tail rotor blade pushes air in the direction shown in the top view of 7.1 as down the page. Remember these two pieces of information, top view of 7.1 and down the page. Now let's jump over to that page. We see that we have the top view of 7.1 and the tail rotor pushes air downward. Because the tail rotor pushes air downwards, that means the thrust that is generated on the helicopter body is upwards from this point over here. This thrust causes a moment on the helicopter body about the rotor head to be anti-clockwise. Now, since the total angular momentum of the entire body increases in the anti-clockwise direction, and because we know the helicopter body stays still, that must mean that the rotor blades spin in the anti-clockwise direction. And that concludes part D. Lastly, for this Ingenuity helicopter, we see that there's no tail rotor. Now, the key difference over here is that the two rotor blades over here spin in opposite directions. Their angular momentum can cancel each other out, and that means that the main body of this helicopter can have no rotation and the entire body can have angular momentum of 0.